So this is the base and the height when we have that integral for the area, okay? And remember that when we drew the individual rectangles here, that that base, right, the length of that base is like a tiny amount or change in the x-axis, right? Well, now we're going to expand this to find volume. Well, how do you find volume of a shape? It's basically the area of a base times the height, correct? Right? Well, if you have to find the volume of a solid that is originated from what we call an integrable cross-section area, okay? The volume is a of x dx in the integral from a to b. Okay, so that's like the basic premise. So now let's talk about how we're going to find the volume of a shape that we're talking about. Okay? All right, so what we're going to do is this. Let me show you this. Okay. All right. So let's talk about volumes by cross sections. Okay? Now, suppose you've got here the x-axis and the y-axis, and you've got a function here, y equals ln of something something, right? This red function. And then you've got another function, y equals b. You want to find the volume of the region of the solid inside these two graphs. Okay, and you're going to do that by cross sections, huh?
What's the height there?
Well, that's what we're going to talk about now. So what we're going to do, this is what we've always seen, right? This is how we've always seen graphs. What we're going to do is we're going to now lay it flat on a table, on a horizontal surface. When you do that, that's what it looks like, correct? On top of this now, I'm going to draw a shape. It could be a square, it could be a rectangle, it could be a triangle. You will be told that shape. So I'm going to draw a square. Do you see that square? One side of the square is lying in the plane of the graphs, and the rest of the square is, three-dimensionally up above it. Okay? All right, now, if I were to ask you, what is the length of that side of the square? How would you be able to find it? What is that length? How do you do it? This length here. The side, huh? Well, yes and no. So what is this? So it starts from y equals 6, and it goes to this function, y equals that ln, right? So this distance here, would you agree that that distance is y1 minus y2? Yes? That's what we were doing before, right? Okay, so now that's one square. Okay? Now, we're going to draw a couple more squares. Like this. Do you see that? So stretching from the very beginning of the region all the way to the end of the region. Do you see how the squares, because they're squares, since one side is getting bigger, the whole square is getting bigger proportionally. And now we're going to make a shape out of this. And if you continue filling this in with a whole bunch of square slices like this, and if you fill in the entire region from here to here, what you get is this. You see that? So now the volume that we have to find is the volume of this shape. And so the lingo here is that this is the solid, okay? Or it's the volume of the solid found by cross sections of squares along the region, okay? Cross sections of squares along the region. All right? Make sense? a little. It's very, very difficult to visualize. That's why, I do my best to, do things like this. So let's move on here to what we were doing before.
It makes sense, but I just can't believe it. Like this is not...
I know, right? You never would have thought.
Yeah.
I know. So look at that. We're expanding. Okay. So how to find volume by the method of slicing. So you want to sketch a typical cross section, just like we did over there. Okay, with the square. Find the formula for A of X. So do you remember that square over there? You have to find here, let me put this side by side here. Okay, so you want to find the area of just one of these squares. Okay, and we already figured out what the side was. Okay, the side is y1 minus y2, and the area is just the square of that. Okay.
And could you also do it like the y instead of like?
No, well, you will be told how. There's only one possibility. Okay. Okay, so here you will be told if the cross section is perpendicular to the x-axis, then the cross section length, like the side of that square, remember how we did y2 minus y1? It's the upper curve minus the lower curve, just like we did before. And then if they're perpendicular to the y-axis, just like we did before, it's going to be the right minus the left. We find the limits of integration, and we integrate A of X to find the volume. So here we go. Let's take a look at our very first one. A solid lies between planes perpendicular to the x-axis from x equals 0 to x equals 4. The cross sections, which are, so here we go. The cross sections are squares with bases in the xy plane are perpendicular to the x-axis. So let's just try to figure out what that means. This is the diagram, or this is the graph that you're most used to seeing. Okay? Now, we were just told that the cross sections are squares, and look, I have a square here. The cross sections are squares with bases in the xy plane. So where's the base of the square? Here. Okay? The base is in the xy plane perpendicular to the x-axis. So like this. You see that? And you've got like a series of squares of different sizes perpendicular and coming out of the page like this. And so that shape that we get, like I just showed you, that's the volume that we're going to find. Okay? All right. So, continuing. And so they run from y equals negative root x to y equals root x. So just like I showed you here, right? It goes from y equals negative root x to y equals root x. Find the formula for the area of one cross section and use it to find the volume. Okay. So what you want to do first is draw a typical cross section. So draw one square inside the shape. Most of the time you're going to be given this. This is only for now because we're learning, right? So basically this will be a representative square. All right. That same square, when I draw it here, because now this is two-dimensional, this side, do you see that base of the square? If I now do a two-dimensional drawing on the bottom one, that's going to be this one. So you're just going to do a random drawing, okay, of one of the cross sections. And it's very important to draw the side of the shape that is acting as a cross section here. Okay. Another thing I like to do is I draw the shape here. I have a square right there, square. The side that's in my diagram is this one. Okay? So now I need to figure out how much that red base is. Well, we just said that if they're perpendicular to the x-axis, then you're going to get the upper curve minus the lower curve. That's that distance. So this is root x minus negative root x, which is 2 root x. Okay, that's how big that side is. Okay, so now, can we find the area of that square? It's 2 root x squared, which is 4x. Okay, now we need to find the volume of this. Okay, so if we go back here, I think these are better ones. So if you go back here, hey, what happened? Okay, do you see how each one of these things, each one of these squares, all right, it has that base, and do you see how each one of these squares also has a little bit of a thickness to it? So if I wanted to find, so now if there's like a little bit of thickness to it, right? So suppose, if it's like something like this, then the volume of this would be the base times the thickness here, right? The base area times the thickness here. And so that, the way we're going to find that is the dx. That little thickness is the dx. So now that finds the area, the volume of this one. Okay, so the area times the little thickness is the volume. And that's the volume of one of these tiny little squares, but eventually I'm going to have an infinite number of them. So one volume plus another volume, that's an integral, and it fills my entire shape. Okay? Integral is from 0 to 4, a of x dx, always. And this will be 2x squared from 0 to 4, and that eventually will be 32. Okay? Now, another one you could do. Yeah. No units, just like area. Okay, another thing you could be given is, okay, same situation now. Now, we're going to be finding use the same base as example number 1, but now cross sections are semicircles with diameters in the xy plane and perpendicular to the x-axis. Okay? What does that look like? Well, I'll tell you what that looks like because I have it here. Now they're going to be semicircles. Do you see that? Hey, where did it go? Right? How fabulous is that? So this is pretty much what we have, right? And so now we have semicircles, and look, you see how these are, like each of them are the cross sections here. So do you see that? And by doing like a series of semicircles, you now create a different shape with the same base. So the volume of this is going to be different. Like, how beautiful is that? Right? You can generate like a whole world of different shapes, right? So now, okay, so do we know how to find the area of a semicircle? Of course we do. It's half times pi r squared. Well, can I figure out the radius from here? Yes, I can figure out the radius because it's this, right? So the radius of each semicircle, if I were to take one semicircle, the radius of it is just from the x-axis to the curve, which is just y, right? Right? Y. No. y2 minus y1 would give you this whole thing. The radius is just this, and it's just this. Okay?
But in this case, wouldn't it be the same because it's symmetric about the axis?
You could do that and then divide and then multiply. So you have to account for the two somehow. You could, I see what you're saying, like,
because in this case it's symmetric about the axis, so it would be half y minus 1.
But if so,
it would just y would be root x, and half of 2 root x would also be root x.
but then you're gonna square it too, because it's pi r squared.
Yeah.
Yeah.
I'm saying define r.
But you're saying to find R would be what?
Just to strictly find R, you're saying it's y.
Yes.
I'm saying why wouldn't it be y1, y2 minus y1?
Because that's
half,
2y.
times a half.
Oh, yeah.
Yeah.
It's the same. Yeah, it's the same.
Okay.
It would still be root x. I see what you're saying. Okay, yes, you could do that. Okay, so it works in this case if they're the same curve. Yeah, but they're different curves. Yeah. Huh?
Could you explain the y?
I'm gonna explain it again. So I'm gonna draw it here again. So we have y equals root x, and then y equals negative root x, and again we're going from 0 to 4. Okay, so here's how I do this. The cross sections are semicircles. So I draw a semicircle up here with diameters in the xy plane. So the diameter, this entire diameter is in the xy plane, and it's understood that it goes along the whole length of the curve, okay, or the region. Now, so we need to find the area of the semicircle, okay? So you can do this in two different ways, right? So one way is the diameter of this whole thing, just like we did before, was 2 root x, remember? Like how we did it here? That length is 2 root x. So the radius is 1 root x because it's half of that. Right. But also what you could do, yes, absolutely. But also what you could do is you can just find the radius immediately. And where does the radius start and end? It starts at the x-axis and goes up to that curve. And remember back in like chapter 4 or 5, we would find that that's just equal to y. Okay? Anytime, because what's y? Root x. So anytime when it goes from the x-axis to the curve, that length is y.
Oh,
Yeah. Okay. So area then is half pi root x squared. So a of x is pi over 2x. And then, so now we're done. So volume goes from 0 to 4, pi over 2x dx. So that's going to be pi over 2, x squared over 2, from 0 to 4. So here are those integrals again, and that's 4 pi, okay? You can never get away from those integrals. And so, sorry, I'll step away for a minute. So the thing is, so on this test, you will have some integrals that you have to do by hand and some that you can use your calculator on. All right, so next one. Okay, thank you. A solid lies between planes perpendicular to the x-axis from x equals -2 to +2. The cross sections, which are isosceles right triangles this time, with bases in the xy plane, are perpendicular to the x-axis, and they run from y equals 4 minus x squared to y equals 0. Okay, so let's just draw this. What shape is this?
That's a semicircle.
Semicircle. So, oh, that's what that looks like. Okay, I could draw a better semicircle than that. -2 to 2. Okay, we're cool? Now, always draw the cross section. I highlighted the cross section. It's an isosceles right triangle. So let me draw that, an isosceles right triangle. This is why we teach you geometry, okay? With bases in the xy plane. So one of the bases is in the xy plane, perpendicular to the x-axis. Do you see that? Okay, so do you see how I transcribed everything I'm reading here? So, you know, if you have like a series of them, that's how they would look. So imagine like taking this, right, by the hypotenuse and like you just sort of like, you know, arrange them here.
Oh, it's the hypotenuse. No, it's
The base. No, that like, so if I grab this here, like, you know, and just sort of like,
Yeah.
you know?
Yeah.
This was always so hard for me to visualize when I was in AP Calc. And then it wasn't until like in May that I really like got the understanding that I had as an adult. You know what I mean? Like that I took with me anyway. So they're hard to visualize. Okay, so let's find the formula for the area. So the formula for the area of the triangle is half times base times height. Okay, so how much is this distance here?
Just y, no?
Just y, which is the square root of 4 minus x squared. So anytime you go from the x-axis to the graph, it's y. And this is also the same. So the area, a of x, is half of this thing squared. Okay? So this is half of 4 minus x squared. And then I like to write this like this, 2 minus x squared over 2, because I'm going to integrate. And now, okay, so the volume is the integral from negative 2 to 2, 2 minus x squared over 2 dx. Okay, now here we can do a little bit of, saving some work here. Okay, so do you see how this is a symmetric region? And I can basically just integrate this half and multiply it by 2, and I get the same integral, right? So that's what we're going to do. I'm going to do 2 times the integral from 0 to 2, because man, if you can ever like switch out a bound for a 0, do it. Okay, so this is going to be 2 times 2x minus x cubed over 6, 0 to 2. This is going to be 4 minus, what is that, 4/3? And that's 16 over 3.
What did you do to put that 3 to 2?
Huh?
What did you do to put that to like 3 to 2?